So we've learned about the Lewis model, and it is an oversimplification, but it's really useful because it works much of the time. There are more advanced bonding theories. We're going to talk about two of them, valence bond theory and molecular orbital theory. These are quantitative approaches, but we're just going to look at them in a qualitative manner. We're not going to do calculations. But there are a lot of, there's a lot of hairy math behind these, and it all works out pretty well. So in valence bond theory, we think of a chemical bond as being an overlap between orbitals. So we know that electrons reside in orbitals that are localized on individual atoms, and we looked at the shapes of those, the s, the p, the d, and the f orbitals. So those exist, but we could also hybridize the orbitals, sort of mash them together and come up with some different orbitals. So we can have hybridized atomic orbitals. So we're blending two or more different kinds of atomic orbitals. Like you could blend an s orbital and a p orbital and have a hybrid orbital. These are all on that one atom. So the idea here is that when two atoms approach each other, the electrons and nucleus of one atom are going to interact with the electrons and nucleus of the other atom. And valence bond theory is looking at the energy changes that result from these different interactions. If the interactions result in a lowering of energy, then a bond will form. If they do not result in the lowering of energy, a bond will not form. So here we can look at, this is energy going up, this would be 0. This is negative energy, which is more stable. Here we have two hydrogen atoms, and on the x-axis we're looking at the distance between the two hydrogen atoms. So here we have them rather far apart, and there's a little bit of attraction, but it's pretty weak. As they get closer together and their orbitals overlap, the attraction increases, the energy decreases. And we keep going and we get to a point here, a distance, where we have maximum attraction, minimal repulsion. And so this is a low energy point. If we push those hydrogen atoms closer together, now the nuclei are getting too close and they're going to repel each other. So you keep pushing them together and then the energy goes back up. So you can imagine what would happen if you had a ball, if this was a hill and you had a ball here, it would roll down and it would end up here, right? If you had a ball over here, it would roll down. Things go to low energy. That's potential energy due to gravity, but it works the same way with this potential energy due to the interaction of charges. So these blue clouds here are the 1s orbitals. The orbitals can overlap, and that causes a lowering of the energy. When we get too close, though, then it increases. It's a little bit like, I think of this as two people, and you're like, oh, well, you look kind of interesting, and so you get a little closer. I'm like, yeah, you're really interesting. And then they're like, this is great. And then you get too close. It's like, no, wait a minute. You're like one of those close talkers, right? It's like you're in my space. You're too close, right? And then you want to move away. And so there's this ideal space between people, right? Does that make sense? So that interaction energy is usually negative when the interacting orbitals have a total of 2 electrons. They could be 1 from each orbital or 2 from one orbital, and the other could be empty, that can spin pair so that they can line up with opposing spins. Because why would electrons be attracted to each other? They're both negative, right? But there's that spin business. The reason that 2 electrons can be in the same orbital is because they spin pair. When 2 orbitals containing 1 electron each overlap, if those electrons can spin pair, then we get a reduction in energy. So usually the electrons come from two half-filled orbitals. Sometimes you can have two electrons from one orbital and an empty orbital from the other atom. That's called a coordinate covalent bond, where one atom is donating both of the electrons for a bond. So valence bond theory, we're looking at two half-filled orbitals approaching, one from each atom. The orbitals overlap, and the electrons spin pair. That results in a lowering of energy. So this is just summarizing what we've said. Valence electrons are in quantum mechanical orbitals. Chemical bonds are the overlap of two half-filled orbitals with spin pairing of those two valence electrons. The geometry of the overlapping orbitals is what determines the shape of the molecule. Okay, so let's look at an example here. We've got sulfur and hydrogen. So we're going to look at the orbital diagrams for the valence shells. So here's sulfur. This is its orbital diagram. It's got 6 valence electrons. So we're going to have two half-filled orbitals here, the 3p. So this 3p orbital could overlap with a half-filled orbital on hydrogen, the 1s. And those electrons can spin pair, and we can form a bond. This other half-filled p orbital can overlap with another hydrogen. The electrons spin pair, and we form a bond. So if it's as simple as that, here's the the sulfur atom, and this 3s orbital is not doing anything. It's just sitting there with its pair of electrons. And then these 3p orbitals, one is up and down, one is out this way, and the other's out that way, right? That's the geometry of the p orbitals. So we have, this one is full, that's this guy right here. These two half-filled orbitals are this one and that one. So half-filled orbital overlaps with hydrogen, those electrons pair up. Half-filled orbital from sulfur overlaps with hydrogen, that fills space, yeah, does that. Spin pair, that's what it is. So if this is exactly how it worked, then this angle here should be about 90 degrees, right? Because that's the angle of the p orbitals. If we look at VSEPR theory, which we just got done studying, and we look at the Lewis structure for this molecule, how many electron groups on the sulfur? 4. 2 lone pairs, 2 bonds. 4 groups. 4 groups do tetrahedral. Tetrahedral, 2 lone pairs, it's going to be bent. So VSEPR theory predicts that the angle between the hydrogen-sulfur-hydrogen, it won't be a perfect tetrahedron. It should be less than 109.5. Well, when we look at the actual bond angle, it's 92. So it agrees with VSEPR theory. It's not quite right with what we're doing here. Let's look at another example. Let's look at carbon and hydrogen. So here's hydrogen's orbital diagram. Here's the valence shell for the carbon. We see that carbon has 2 half-filled p orbitals. And so we could overlap one of these with one hydrogen, and the other one could overlap with another hydrogen. And so that's what we're illustrating here. This third p orbital is empty, and so we didn't draw it. So these would be oriented at right angles to each other. This would overlap with hydrogen, and this one would overlap with hydrogen. We would predict that there's a 90-degree angle there and that the formula is CH2. But that's not what happens. It's actually CH4, and the angles are a perfect tetrahedron, 109.5 degrees. So obviously something is missing here, right? Any questions yet? Well, it turns out the orbitals in a molecule are not necessarily the same as the orbitals in an isolated atom. Orbitals can hybridize. That's a mathematical procedure in which you take standard atomic orbitals and you combine them together to form hybrid orbitals. It's a little bit like taking those wave functions and averaging them together. When we do this, this corresponds better to the actual distribution of electrons in molecules. We're still looking at these electrons and the hybrid orbitals as being localized on atoms, but the shapes are going to be different than standard atomic orbitals, and the energies are going to be different. So what hybrid orbitals do is they minimize the energy of the molecule by maximizing the overlap. So when those orbitals can overlap more, that's a lower energy. When you hybridize orbitals, instead of the electron density being equal on each side of the atom, it's going to become more lopsided and be more on one side of the atom, and so that allows you to overlap better. So what we're going to do is we're just going to look on hybridizing the orbitals on interior atoms, and we're going to leave the terminal atoms unhybridized. That's not actually what they do, but we can ignore the hybridization of terminal atoms. Yes? So interior would be a central atom that's bonded to lots of different atoms, and a terminal is an atom that's just bonded to one. Yeah, so in CH4, the hydrogens are terminal and the carbon is interior or central. We kind of start talking about interior because with a lot of molecules, there's not just one central atom, there's a bunch of them. So general things to keep in mind. You end up with the same number of orbitals that you started with. If you take two orbitals and you hybridize them, you end up with two hybrid orbitals. If you hybridize four orbitals, you end up with four hybrid orbitals. So you could say the number of orbitals is conserved. The particular combination of the regular s, p, d, and f orbitals that you're hybridizing is going to determine the shape and the energy of the hybrids you end up with. And the particular type of hybridization that actually occurs is the one that gives us the lowest energy. Well, since we're not going to do any calculations, because that's way past what we want to be doing, we're going to use Vesper theory to predict what the geometries are, what the hybridization is. Okay, so that's why we're talking about this after Vesper theory. So let's talk about taking an s orbital and three p orbitals and hybridizing them together. So the s orbital is lower in energy, the p orbitals are higher in energy, but when we average them together, we end up with four orbitals that are degenerate. They're all at the same energy. And as you can imagine, the energy of these hybrid orbitals is between the energy of the unhybridized orbitals. So we end up with four hybrid orbitals. And because this is a combination of an s and three p orbitals, we gave it the very creative yet descriptive name sp3. It's got an s and three p orbitals. Okay? So here's carbon's standard atomic orbitals. The s orbital is lower in energy, so two of the electrons go in there, and then we have two electrons that are up in the 2p sublevel. Hybridizing these all together, now we have four orbitals that are equal in energy. And so the electrons will fill these individually before they start pairing up. Does that make sense? So how does this relate to the quantum hotel? Well, in the quantum hotel, what we're doing is we're knocking down the wall between the 2S room and the 2P room. We're remodeling. Okay? And so now you had 3 beds and 2 beds. Now it's all in one big room. And we're going to charge the same amount for each. So you remodel the room, you put the 4 people in there. And now they can each have their own bed. That make sense? So what does this look like? Well, there's the s orbital. There's one of the p orbitals. Here's another, and there's the third one. And we're going to take all 4 of those and average them together. And we end up with 4 things that look like this. They kind of look like drumsticks, right? A small end and a big end. And these are going to be spread out equally in 3-dimensional space, which is a tetrahedron. We can draw them all together like this. We see the tetrahedron. This little end here is not significant. It does not participate in bonding. And so when we draw them all together, we leave that little side out because it makes the drawing really messy. So carbon does this sp3 hybridization a lot. When we draw the hybridized orbital diagram, now we've got 4 boxes together, indicating that they're all the same energy. And it's not S and P, it's sp3. So all of these are the same energy. Carbon's 4 valence electrons. We put them in with parallel spins, each having their own box. Each of these half-filled orbitals can overlap with the orbital from another atom, like hydrogen. So here we have in the purple, because the purple is a red and blue mixed together, right? Here we've got blue, we have blue and red, and when we mix those together, we get purple, right? It's kind of cool how they did that. So you got your hybridized orbitals, and they form a tetrahedron. So now all 4 of those orbitals have the same shape and the same energy. They're just spread out in different directions. Instead of having an s orbital that's a sphere and the p orbitals that are those 2 lobe shapes. So 1 electron in this hybrid orbital overlaps with hydrogen. 1 in this overlaps with another hydrogen, this one overlaps with hydrogen, and that one overlaps with hydrogen. Now this works out much better with what we experimentally observe. The carbon and hydrogen together will be CH4, and the geometry is tetrahedral. If we don't hybridize the orbitals, we can't explain how that happens. Any questions? We can have lone pairs in hybrid orbitals. So here we've got nitrogen. And just for grins, let's look at nitrogen's atomic orbitals and the hybrid orbitals. So here we've got S and P, and all 4 of those together now is sp3. How many valence electrons does nitrogen have? 5, right? So in the atomic orbitals, we're going to put 2 in that s orbital. We're going to have 1 each in the p orbitals. When we hybridize that, we still have 5 electrons, but now we're going to put them into these 4 degenerate orbitals. 1, 2, 3, 4. Each electron in the hotel is going to take their own bed as long as they can. So we get 4 guys sleeping in their own beds, and then the 5th guy comes in. He's got to pair up with somebody. This is the hybrid orbital diagram for a nitrogen atom. And here we see we have 3 half-filled orbitals. Each of these half-filled orbitals can overlap with an orbital from hydrogen. So hydrogen has that 1s orbital that's half-filled. So hydrogen overlaps here, another hydrogen overlaps there, another hydrogen overlaps there. The 4 sp3 orbitals form this tetrahedron in purple. 3 of those orbitals overlap with hydrogens, and the 4th orbital has a lone pair in it. That makes sense? So this is ammonia. We talked about how the angles for ammonia are not 109.5. It's not a perfect tetrahedron. These bond angles are closer to 107, which is going towards the angles of an unhybridized orbital. And the reason for that is because of this lone pair, this hybridization is not complete. It's a little bit iffy. Thankfully, we don't have to get into exactly how iffy it is, but what it means is that these three hybridized orbitals here are a little bit more like p orbitals. They're not all exactly the same, and so that accounts for the different bond angle. Any questions? Yes?
So if you have like NH4+, that means that the hybridized orbital have one less electron?
Yeah, so what if you had NH4+? Well, the plus means that we're short an electron, right? And so the 4th hydrogen coming in would just have an empty box. Should I do it like this? It's missing an electron. So that one coming in would overlap and form one of those coordinate covalent bonds where both of the electrons in the bond are coming from the nitrogen. And then we'd see that we're going to get better angles, but that's how NH4 would form.
Would that be, is covalent bonds synonymous with 4 bonds?
Covalent bonds, no, not synonymous with 4 bonds. We'll see that we can do lots of different things. Say that again. Covalent and polar bonds. Some covalent bonds are polar, some are not. But when we're talking about polar and nonpolar, it's always about covalent bonds. It's not ionic. So let's look at what happens when we have an s and 2 p orbitals hybridizing. So here's our standard atomic orbitals. We'll take the s and just 2 of the p's and average those together. We're hybridizing 3 orbitals. We're going to end up with 3 hybrid orbitals. They will be in energy equal to each other, but between the orbitals that they came from. Because, if you imagine averaging 2 at this energy and 1 at that energy, the average energy of these 3 is going to be in the middle somewhere. This p orbital that didn't get hybridized doesn't change. It's going to sit there. It has the same energy and shape it did before. And we call these sp2 because it's 1 s and 2 p orbitals. So there's s orbital and 1 p orbital and another p orbital. We hybridize those together. Now we've got 3 equivalent orbitals, and they are going to spread out like 3 balloons would in 3-dimensional space, and we're going to get this trigonal planar shape. We're taking different orbitals and hybridizing them, averaging them together, and so we still have 3 orbitals, but now they're all the same shape. They're all the same energy. They're going to spread out in space. So H2CO has sp2 hybrid orbitals. So what happens here is this carbon, here's its orbital diagram as an uncombined atom. We're going to hybridize an s and 2 of the p orbitals into sp2. And so there's 3 there. And then we've got that other orbital that's unhybridized. When we hybridize these orbitals, These sp2 orbitals are going to be lower in energy than the p, but they're not that far away. So as we put the 4 electrons in, 3 of them are going to take their own beds here, and the 4th one's going to say, yeah, but just for like 10 cents extra a night, I could have my own room and my own bed. That's definitely worth it. So a little bit of an energy jump, but this way it can be unpaired, and now we've got all of these half-filled. So energy bonus there. So this is our central atom, and then these orbitals can overlap with the other orbitals. So we've got oxygen and 2 hydrogens. I'm just going to white this out because this is kind of in the way. So the carbon became this, and now we can look at how are these overlapping. Well, we've got 2 hydrogens. So one of the hydrogens can overlap like that. Let's draw the other one. And this one can overlap with that one. And then, oops, that's not what I meant to do. One of oxygen's half-filled orbitals can overlap with this 3rd sp2. And the other one will overlap with the unhybridized p orbital. Here we have 2 orbitals from the same atom overlapping with 2 orbitals from the same other atom. That's going to look like this. You thought the balloons on Monday were weird. So what's going on here? So the purple balloon-looking shapes here are the sp2 hybrid orbitals. You take 3 orbitals, you mash them together, you've got 3 that are the same shape, and they're going to spread out just like 3 balloons would, and so you get this trigonal planar arrangement. Each of those orbitals on carbon has 1 electron in it, and so we can have one of those orbitals overlapping with a hydrogen, and this other one overlapping with a hydrogen, and the 3rd sp2 hybrid orbital overlaps with a p orbital on the oxygen. We still have an unhybridized p orbital on the carbon and an unhybridized p orbital on the oxygen, and those overlap in a side-to-side way. It's important to understand that the red part down here and the red part up here is not 2 separate things, because this p orbital is on both sides, which seems kind of weird. How can the electron be on both sides? Well, it's a standing wave. And so the carbon in the middle is like the node, and you've got the standing wave on both sides. And here we've got the standing wave here overlapping with the standing wave over there. These bonds, well, let's look at this one. This one's easier. Here we've got this sp2 hybrid orbital, which is this sort of balloon shape. And then we got this p orbital here, and they're overlapping end to end, right? Overlapping end to end. We call that a sigma bond. And the p bonds here are overlapping side to side, and that's called a pi bond. So we've got 1 sigma bond and 1 pi bond between the carbon and the oxygen. That's 2 bonds, that's a double bond. The carbon has 2 bonds with oxygen. One is the overlap of a hybrid orbital with the p orbital on the oxygen, and the other is the side-to-side overlap of the unhybridized p orbital on carbon with a p orbital on the oxygen. Any questions? Let's talk more about that pi orbital. The pi bond. So here's 1 half-filled p orbital and another half-filled p orbital. those can overlap. These lobes overlap. And these lobes overlap. And so it's going to look something like that. That's side to side. This is 2p orbitals overlapping end to end. And so this lobe and that lobe overlap, and we get something that looks like that. If you look at this from the end, it's just going to look like a circle, right? Looking down the end from this point to this point, you're just going to see a round circle. That's a sigma bond. This is a pi bond. Pi, turn on side. Pi bond. So pi bond is side to side, sigma bond is end to end. So here's that same molecule. We can label these bonds. So this bond here between the hydrogen and the carbon, on the carbon we have an sp2 hybrid orbital participating, and on the hydrogen we have an s orbital. And so we can label that bond as sigma C sp2-HS. So this is a sigma bond, an end-to-end overlap between carbon and hydrogen. The orbital on carbon is sp2, the orbital on hydrogen is s. So that describes this bond. It also describes this bond. They have the same description. This bond in the middle is a sigma bond, end-to-end overlap, between carbon and oxygen. On the carbon, we have an sp2 hybridized orbital, and on the oxygen, we have just a regular p orbital. This pi bond, the side-to-side overlap, is also between carbon and oxygen, but it's an unhybridized p orbital on the carbon and an unhybridized p orbital on the oxygen. On the worksheet we're doing in lab today, you're going to have to label the orbitals like that. So we get more information, more insight with valence bond theory than with the Lewis model. In valence bond theory, we see that the double bond between carbon and oxygen is actually two different kinds of bonds. Whereas in the Lewis model, it looks like it's two identical bonds. Whenever we see a double bond in the Lewis model, it's always a sigma and a pi bond in valence bond theory. Pi bonds are weaker. You can kind of imagine that. This side-to-side overlap is, not as strong. This pi bond is weaker than the sigma bond. And experimentally, we observe that when you start breaking that double bond, the pi bond breaks first, and then the sigma bond, because the sigma bond's harder to break. This also explains rotation around bonds. Here we have two similar molecules. We have 1,2-dichloroethane, and we have 1,2-dichloroethene. The difference is this one has a double bond between the carbons. This has a single bond between the carbons. The single bond is a sigma bond, and you can imagine that we could rotate. Here we have a double bond, we have a sigma bond and a pi bond, and if I try to rotate this side, I can't do it unless I break the pi bond. So for that version with the single bond, we get free rotation. And there's no difference between these structures because they interconvert. At any given point, you could find one that looks like this, one that looks like that, or in between, but they change, they rotate. Here, with the double bond, we can have the chlorines on the same side of the double bond or on opposite sides of the double bond. We call this cis, and that's called trans. Those cannot interconvert. Those are two distinct compounds. Their properties are quite similar. Their molar masses are exactly the same, but their chemical properties are going to be a little bit different. The reactions that occur here are going to be different than those that occur with this one. That's a preview of OChem right there. Okay, what if we take one S and one P? Well, then we're going to get two hybrid orbitals, and it's going to be called SP, and we'll have two unhybridized p orbitals left over. So what that would look like, you've got this s orbital and a p orbital, and you average those together, and you're going to get two of these, drumstick shapes, and they're going to be pointing in opposite directions. The unhybridized p orbitals are still there, because this is using the px orbital. Then the unhybridized orbitals, there'd be the p y and the pz, so they'd be at right angles to each other still. So let's look at acetylene. It says draw the Lewis structure. Just kind of silly, but so there's the Lewis structure. It doesn't really look much different than that, does it? Acetylene has sp hybrid orbitals, and we'll learn in a few minutes about how you could predict that. So here's our carbon atom, these atomic orbitals, and we're going to hybridize. We're going to take an s and one of the p's to become sp hybrid orbitals, and the other p orbitals are just going to be left unchanged. We're going to be drawing diagrams like this in the worksheet as well. So each box represents an orbital. So if we're starting out with 4 boxes, we have to end up with 4 boxes. And again, the p orbitals and the sp hybrid orbitals are similar in energy, and so the electrons can spread out and half fill all of them. So the carbon is going to make 4 bonds. So one of these bonds will be with hydrogen, and another one will be, well, let's see, where am I going with this? And we need another, there's hydrogen and the hydrogen. So here we've got, this is hydrogen, this is carbon, and this is hydrogen. So this carbon, one of its hybrid orbitals can overlap with hydrogen. The other hybrid orbital is going to overlap with one of the other carbon's hybrid orbitals. And then this carbon is going to overlap with hydrogen. The two unhybridized p orbitals from both carbons are going to overlap with each other, forming pi bonds. That looks like it could be some sort of cool pool toy, right? Climb on that. The purple is the sp hybrid orbitals. 2 lobes going in opposite directions. They're each half filled. So one lobe overlaps with hydrogen, the other lobe overlaps with a hybrid orbital on the other carbon. The second orbital from the carbon, other carbon, overlaps with hydrogen. Then we have a p orbital on each carbon in this direction, and a p orbital that's vertical on each, and those overlap side to side. This is a triple bond. There's 1 sigma bond and 2 pi bonds, and that makes a triple bond. It's consistent with the geometry of this molecule. Any questions? Here's the identifying of these bonds. Here's this pi bond, pi, CP, CP. The sigma bond is between sp on the carbon and s on the hydrogen. And this one in the middle here is a sigma bond between two carbons, sp hybrid orbital on each. Now, we talked about expanded octets, right? So elements in the third row, third period or below, third, fourth, fifth period, sixth, seventh, those are elements with their valence electrons on the third floor or higher in the quantum hotel. So on the third floor, there's an S room and a P room, but there's also a D room. Most of the time it's empty, but if we need to, we could put some electrons in there. On the fourth floor, there's also a D room, and on the fifth and the sixth. But it doesn't happen on the first or second because there's no extra rooms. The energies of the 3D orbitals are similar to those of the 3s and the 3p. They're not the same, but they're close. So the expanded octet, now we're not just hybridizing s and p orbitals, we're going to pull some d orbitals into the mix. So here's sp3d. It's always going to, hybrid orbitals are always going to include the s orbital, and then you're going to start with at least one p orbital, or it could be 2 or 3, and then you can add in d orbitals, but you're never going to have just s and d. Because in the hotel, right, there's the s room and the p room and the d room, and hybridizing orbitals is like remodeling and knocking down walls. You can't have s and d together because p is in the middle of it. Right? So you can go through the P room and include some of the D room. So this is sp3d. So that's a total of 5 orbitals. And then those 4 are left unhybridized. So what do 5 things do? 5 balloons make a trigonal bipyramid. Trigonal bipyramid. Made that one yesterday. So here we have arsenic pentafluoride. The arsenic is going to be sp3d hybridized, and so we're showing that here in the orange. I'm not sure why we changed colors now, but it should be purple. So each of those is going to have 1 electron that can overlap with fluorine. So let's just look at these. So for fluorine, the fluorine's going to be unhybridized. How many valence electrons does fluorine have? 7. 1, 2, 3, 4, 5, 6, 7. So there's 1 half-filled orbital. That's this p orbital that's forming a sigma bond with the arsenic. And let's look at the arsenic. So arsenic has 5 valence electrons, right? So one, 2, 3, 4, 5. There are also, though, d orbitals there. They're just empty. This is s, p, and the d's. So arsenic can hybridize 5 orbitals together. We'll take the s, all 3 p's, and 1 of the d's. So now we're going to get 5 that are sp3d, equal in energy, and then we've got these left. So I've got 4 d orbitals that are left unhybridized. I still have 5 valence electrons. So doing the valence electrons now, I'm going to go 1, 2, 3, 4, 5. each half-filled orbital can overlap with the half-filled orbital of another atom. So I've got these 5 hybrid orbitals. They form a trigonal bipyramid shape. Each of these can overlap with one fluorine atom. We learned from Vesper theory to look at this and say there's 5 groups, there aren't any lone pairs, that's going to have a trigonal bipyramid shape. Any questions? Yes?
Would you put the remaining valence electron hybridized?
What remaining electrons? Well, fluorine's not going to hybridize. So actually terminal atoms do hybridize, but that makes everything very complicated, and we don't need that for our purposes. So we're not hybridizing the fluorine atoms. We're just hybridizing the central atom. So these guys that are paired up in the unhybridized orbitals, they're just fine. Any other questions? Well, why stop there? Let's take 6. S, 3 of the P's and 2 D's, that makes sp3d2, right? And so now we've got 6 hybrid orbitals and 3 remaining unhybridized d orbitals. What do 6 balloons do? Six balloons. Call that an octahedron, right? We've got 6 identical hybridized orbitals. They all have the same shape, the same energy. They're going to spread out in 3-dimensional space and arrange themselves like an octahedron. So here we have sulfur hexafluoride. So again, we're looking at fluorine. Fluorine with its 7 valence electrons. We're not going to hybridize that. And so it has 1 half-filled orbital. And we learned that a lot of the time fluorine makes 1 bond. And then if we look at sulfur, I'm going to put sulfur down here so I have more space. Sulfur's in the 3rd period. So it's got s, p, and d orbitals. And how many valence electrons does sulfur have? 6. 1, 2, 3, 4, 5, 6. So we're going to take two of the d orbitals with the s and the p's and make hybrid orbitals. And we're going to have 6. And these 3 d orbitals are still there. They were empty before, they're still empty. So those are the d's, and this is sp3d2. We still have 6 valence electrons. 1, 2, 3, 4, 5, 6. So we have those 6 orbitals, like these 6 balloons. Each one has an electron in it, and it can overlap with the orbital on the fluorine. So each of those can overlap with 1 fluorine, and so we get something that looks like that. This is a sigma bond between sp3d2 on the sulfur and an unhybridized p orbital on the fluorine. The shape is an octahedron. The model matches up with observation. Any questions? Okay, so far I've been saying, well, this is the hybridization it does. How do we know what the hybridization is? Well, you calculate it to give the molecule the lowest energy. We're not going to do that. We're going to do good enough for Chem 1A. We're going to assign the hybridization scheme from the electron geometry on the central atom. Now this is not 100% accurate, but it works most of the time, and that's good enough. So what we're going to do is we're going to look at VSEPR theory. We're going to look at the number of groups, electron groups on the central atom, and that's going to tell us what the hybridization is. So if you have two groups, 1, 2, you need sp hybridization. If you have three groups, 1, 2, 3, you need sp2 hybridization. If you have four groups, 1, 2, 3, 4, sp3 hybridization. If you have five groups, 1, 2, 3, 4, 5, sp3d, and 6, sp3d2. Okay? So it's really not that hard. You start with S, you add as many P's as you need, and then as many D's as you need until you get the number of hybrid orbitals that's equal to the number of electron groups. Any questions? So, instructions for writing hybridization and bonding schemes. Start with the Lewis structure. Use VSEPR theory to predict the electron geometry, the number of electron groups. You're going to select the correct hybridization based on the electron geometry. If you've got 4 electron groups, it's going to be sp3 because you need to hybridize 4 orbitals. Then you sketch the molecule. Start with the interior atom and its orbitals, and then show how those overlap with the orbitals on the terminal atoms. And you label the bonds using sigma or pi notation, followed by the type of the overlapping orbitals. Write a hybridization and bonding scheme for XeF4. Well, we have to start with the Lewis diagram. So we'll start with xenon in the middle and fluorines around it. We have to consider the number of electrons. Xenon has 8, and we have 4 fluorines, and they each have 7. So I think that gives us 36. I've got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. We have 4 more electrons. Where do I put them? On xenon. Xenon can expand its octet. 34, 36. Okay, Lewis structure for xenon tetrafluoride. We look at the central atom and we ask ourselves, how many electron groups? 6, right? 6 electron groups. So, sp3d2. That's 6 fingers. Okay? So the hybridization is sp3d2. Six electron groups means sp3d2. So what you're going to be doing on the worksheet, you're not going to draw the picture. I'm going to draw the picture. It's going to be ugly. You're going to look at just the orbital diagrams. So the orbital diagram for xenon, we're going to have sp3d2 hybridization. Now, I thought I was doing 5. There. 6 boxes, right? And then we can't ignore the other d orbitals. How many d orbitals are left? There were 5 to start with, right? And we took 2 to hybridize, so we got 3 left. So there's d orbitals just sitting there empty. And this is sp3d2. How many valence electrons does xenon have? 8. So I'm going to put 8 valence electrons in here. 1, 2, 3, 4, 5, 6, 7, 8. What do you know? I've got 2 full boxes here. those are the two lone pairs. I've got 4 half-filled hybrid orbitals. Those are the ones that can overlap with an orbital on the fluorines. So fluorine, we're not going to do hybridization for the fluorine. Fluorine has 7 valence electrons. It's going to look like that. This is S, this is P. So it's this half-filled orbital on a fluorine that's going to overlap with one of those. So now I'm going to attempt to draw a picture. So let's put xenon in the middle. And xenon has 6 hybridized orbitals, right? So there's 1, 2. This one's coming out at us. 3. That one's kind of going back. 4. Kind of going back. 5. This one's sticking out. 6. Well, that one's a little too big. So these 2 are sticking out at us. Those 2 are in the back. This one's up and down. So each of these has an electron. But 2 of them are full, right? Does it matter where we put those? Yeah, it doesn't matter where we put the first one, but it matters where we put the second one. So I'm going to put the first one up here, and then the second one's going to be opposite because they want to have their own space. So then we've got the fluorine. We'll make the fluorine green, I guess. So fluorine, we're not going to draw all these lone pairs because that's going to make a big mess. I'm just going to draw this half-filled p orbital for fluorine. So there's one fluorine, and here's another one. And here's another one. Oops, missed. Each of those had 1 electron in it, and so those are going to pair up. We need to be able to label these bonds. So you're going to do things like drawing orbital diagrams on that worksheet. I'm not going to make you draw pictures like that, but we need to be able to label the bonds. So here, all of the bonds are the same, right? We've got a sigma bond, end-to-end overlap. So sigma bond between xenon and fluorine. And what's the orbital on xenon that's overlapping? It's the hybridized orbital, right? sp3d2 is overlapping with fluorine, and we're assuming that the terminal atoms are unhybridized, and so that's this p orbital on the fluorine. Any questions? Let's do HCN. We start with the Lewis structure. There it is. We look at the central atom and we ask ourselves, how many electron groups? A triple bond is one group. A single bond is one group. How many groups? 2 groups. So what's the hybridization? sp. Okay. So for that carbon, we're going to have sp hybridization, and then we also have 2 unhybridized p orbitals. Okay with that? So that's the hybrid. This is the atomic. if we put electrons in there. 1, 2, 3, 4. When we hybridize them, though, they can all have their own orbitals. So we've taken these two and hybridized, and we've got these unhybridized p orbitals that are left. Hydrogen's nice. This hydrogen is very simple. So it's got that s orbital with one electron in it. So we're going to have overlap between this half-filled orbital on the hydrogen and one of the hybrid orbitals on the carbon. Over here, we've got a nitrogen. So let's do nitrogen. There's nitrogen with its S and P. Nitrogen has 5 valence electrons, 1, 2, 3, 4, 5. This other hybrid orbital on the carbon is going to overlap with something on nitrogen. Well, it's going to have to be one of those unhybridized p orbitals. We've got a triple bond here. A triple bond is going to be 1 sigma bond and 2 pi bonds. Pi bonds are always between unhybridized p orbitals. P, pi. So those are going to overlap and these are going to overlap. Okay, so let's try to, this is actually a little easier to draw. Here's my carbon in the middle. There's one sp hybridized orbital and another sp hybridized orbital. And then it also has unhybridized p orbitals. The nitrogen over here has unhybridized p orbitals. It's got 3 that are half-filled. Let's put some electrons in there. So I've got an electron here, an electron there. I've got one here and one in that one. Dosary issue. Dosary issue. So here we have end-to-end overlap between one of the half-filled p orbitals on the nitrogen with the carbon's hybrid orbital. Over here, the other hybrid orbital for excuse me, for carbon is going to overlap with hydrogen's s orbital. There's 2 electrons there. And then we've got these unhybridized p orbitals. There's a half-filled one on the carbon and a half-filled one on the nitrogen. Those are going to overlap side to side. So that's 1 pi bond. And then this is another pi bond. Isn't that a lovely mess? Yeah, I dare you to do better. So we need to write bond descriptions. So let's start with this one. Is that sigma or pi? Sigma. So we got a sigma, and it's between carbon and hydrogen. And what's the orbital on carbon that's involved? It's the sp, right? An sp orbital on carbon is overlapping with hydrogen, and what's hydrogen got going on? Just an s. And then we've got a bond here. Is that one sigma or pi? sigma. So that's between carbon, again, that's one of the sp hybrid orbitals, overlapping with nitrogen's p orbital. Nitrogen's p orbital. Then I've got a p orbital on carbon overlapping side to side with a p orbital on nitrogen. So that's a pi bond. So C, P, and P. And I've actually got two of those. There's this one, and then there's this one sticking in and out. Any questions? Everybody's looking at that and thinking, I have no idea what's going on. She's asking if I have a question. I have so many questions, but I can't actually put any of them into words because I'm not to that point yet.
Why is it SP for the carbon and only P for the nitrogen?
That's a good question. Why is it an unhybridized p orbital from the nitrogen? Why isn't this hybridized? Because we're trying to make it easier for you. This is a terminal atom. The carbon's in the middle. So we are only going to look at hybrid orbitals on the central atom. We're going to assume that this one doesn't hybridize. It does a little bit, but we can ignore it, so we're going to. Does that help? So when I drew this orbital diagram for nitrogen, I'm just doing the regular atomic orbitals, S, P, D, if there were any. And we'll look at these half-filled orbitals, and those are the ones that are going to overlap. What happened to this one? Well, that's an s orbital that I didn't draw. That'd be this s orbital in here, and that's where that lone pair is. Any other questions? Yes? Can I do an example with a charge and a lone pair? You mean like the ammonium?
Or like CLF plus?
Yes, you just throw in an extra electron. I can. Let's see. See if I have one of those. No. So what did you want? CLF 4 plus? Oh, CLF 4 plus. I'm like, that one looks really weird. Okay, well, let's see what this does. Gotta start with the Lewis structure. Chlorine in the middle. 4 fluorines around it. Counting up electrons, we have 5 times 7, 35 electrons minus 1 because of the positive charge, so 34. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. 2 more electrons, where do I put them? On the chlorine. There's 34. The correct Lewis structure would have brackets and a charge on it. So here's a question. There's got to be a formal charge. Who's got the formal charge? The chlorine. The chlorine has a +1 formal charge. Okay, so let's look at the individual atomic orbitals. We'll do fluorine first. The fluorines are not going to hybridize. So we've got S and P. They've got 7 electrons, 1, 2, 3, 4, 5, 6, 7. And then we'll look at the chlorine. I'm going to start down here. 1, 2, 3, 4, 5, 6, 7. But it's got a positive 1 formal charge. That means I have to remove an electron from the chlorine. So back that up. There's 6 electrons for the chlorine. Okay, so now we have to predict what hybridization is it. How many electron groups are on the central atom? 5. sp3d, right? So we're going to do sp3d. I do this in purple. So here's chlorine, and we're going to have 5 equivalent sp3d orbitals. And then we've got these 4 that are left over, right? Those are Ds. And this is the sort of thing you're going to be doing in the worksheet. If you do it horizontal like this, or if you want to put the Ds above because it fits in the box better, I'm okay with that. But we need to conserve boxes, we need to conserve orbitals. So for this atomic orbital diagram, because we're going to use the d orbitals in the hybrid, then we need to include them here so that we don't see new boxes appearing out of nowhere. So then the chlorine has 6 electrons, so we're going to put those in here. 1, 2, 3, 4, 5, 6. And look how that matches up nicely with this. We have 1 lone pair and 4 bonds. We have 1 full orbital, that's the lone pair, and we have 4 half-filled. Those are going to be the bonds. Somebody just saw the light. So each fluorine is like this. So that can overlap with 1 of the orbitals on chlorine. And this one will overlap with another fluorine, and this is another fluorine, and this is another fluorine. And then this is the lone pair. And so we can do the bond notation. So we've got a p orbital and an sp3d orbital. That's going to be a sigma overlap between the chlorine. And on the chlorine, we've got the sp3d. And on the fluorine, we've got just a p orbital. Is that good enough?
Yeah.
You don't need the messy picture, right? No. Any questions? Okay, now we're going to do CO2. So CO2 Lewis structure looks like that. We'll draw the atomic orbitals. So for oxygen and for carbon, oxygen has how many valence electrons? 6. 1, 2, 3, 4, 5, 6. You see those 2 half-filled orbitals? Oxygen likes to form 2 bonds. It uses both of those. Carbon, 1, 2, 3, 4. We don't see the 4 bond thing there, but there's going to be some hybridization, right? How many electron groups on this carbon? 2. So hybridization is sp. So we're going to take an S and a P. And so for the hybrid carbon, we're going to have sp, and we're going to have the remaining unhybridized p orbitals. Still 4 electrons. This one gets a little weird. So what I'm going to do is I'm going to draw the other oxygen as well. So here's S and P for the other oxygen. so we can see what's going on here. So the hybrid orbitals, we're going to take care of those first. So one of these is going to bond with one of the oxygens, so we get an overlap between these two guys. Because these double bonds, we have to have one sigma bond and one pi bond. And this other one is going to overlap with one of the unhybridized orbitals on the oxygen. Then I've got two unhybridized p orbitals here, and I've got unhybridized p orbitals on those oxygens. So these are sigma bonds. And then we're going to have pi bonds with those guys. I'm going to draw this one. Need some space. Okay, so here's the carbon. There's one sp hybrid orbital, and there's the other sp hybrid orbital. It also has an unhybridized p orbital and an unhybridized p orbital. And then I have oxygen. So here's oxygen, and it's got unhybridized p orbitals. I'm not going to do its lone pairs. So this is the overlap between a sigma bond on the carbon, a sp orbital on the carbon and a p orbital on the oxygen. So that's a sigma, carbon, sp, oxygen, p. And then I've got a pi bond between the carbon and the oxygen. So that's pi, carbon with a p, oxygen with a p. So that's part of it. Then over here, I've got the other oxygen. P orbital and p orbital. So here I've got that sigma carbon sp oxygen p. That's that guy right there. And then I'm going to get a pi bond here. Here's carbon's other p orbital, the one that's sticking in and out, and that's going to overlap with this one. It's also a pi CpOp. Any questions?